Thanks. I absolutely cannot see anyone because of the lights, so I'm glad to know you're all there, actually. That's great. So one of the things that I like to talk about when I'm talking about IoT data, first of all, when anybody talks about IoT, they tend to talk about how many devices we're connecting to the network, right? There are going to be 20 billion devices, there are going to be 40 billion devices. But the problem with talking about the number of devices is that it ignores one of the main problems with IoT, and that is the data that comes out of them. So for every device, IoT device that you connect to the network, you're going to typically get anywhere from 1 to sort of 15 or 20 data streams, and those data streams, once they're turned on, are never going to turn off. So when you're talking 20 billion devices, you're talking sort of another order of magnitude or so number of data streams. So that's really the problem that needs to be addressed with IoT more than anything else. And when you're talking about collecting that amount of data, you really need to start to think about where you're going to collect that data. Are you going to collect that data at the edge, or are you going to collect it all in one central place? And there's a lot of things that need to go into deciding how you're going to divide that up. A lot of it is going to be how the data is used, who's going to be using the data, how they need to access it, how they need to visualize it, what sorts of actions are going to be taken on that data, right? So if I'm going to send all my data to a back-end service, then I need to make sure that I have the right sort of network connectivity and the right sort of ways to partition my data in the back end so that the people that need access to that data can have access to that data, right? So if I'm going to collect this in a cloud-based service somewhere with no edge collection at all, it means that all of my devices have to have full-time internet connectivity. And this can be a problem. This can also be really expensive. It requires highly available networks from the edge all the way, not even the edge, but from the device all the way back to the cloud. Sometimes this is completely impractical. For instance, if you're putting IoT devices on an oil drilling platform in the Gulf of Mexico, right? They use a satellite uplink, and there's high latency, low data throughput, and it's really expensive. So having all of your data go to the back end and then have to send it back down to the oil platform for operators to visualize and take action on it isn't really practical, right? The upside is that you can do your analysis and visualization from anywhere, but the downside can be high cost, high latency, and catastrophic failures. If you can't get your data to the back-end platform for analysis, then you can't notice when pressure in a valve is extremely high, and you may miss when the oil platform explodes. Well, you won't miss it, but you'll be notified in a rather abrupt manner that your oil platform has had a problem. The other option is, of course, to collect it all at the edge, and that's mostly what I'm talking about here when I talk about this ability to collect your data anywhere. So you're going to collect your data close to the sensor, right? That way you have very low latency from sensor to collection platform. You can have this sort of deployment on an unreliable backhaul network, and you can do a lot of local processing and analysis without having to upload data over the internet to a back-end service. This can reduce costs, it reduces latency, but then you have these issues of, well, people in the back end need access to my data, and it's all down in various edge collection devices, and so somehow I still have to manage getting data back upstream. And this is where you get into sort of having to build a larger architecture for data collection. So I'm going to collect at multiple points, I'm going to collect at multiple edge points across the network, and then I'm going to have to figure out how to aggregate that data back up to larger collection points and finally up to a data lake somewhere so that I can have access to all of my data from all of my collection and all of my sensors from one place. Right? And this is, of course, more tolerant of network outages because if the network's down between 2 points, then at least I'm doing my data collection and analysis at my local point, and I can still make sure that my oil rig doesn't explode, but there's delays in sort of the larger back-end processing of this data. It does distribute the data collection load, and if you do it this way, you can also distribute the data analysis and data visualization load. What this allows you to do is give local operators access to the data that they need. Remember I talked about you need to decide who needs access to what pieces of data and how they're going to visualize it. So if you're doing these local collections, local analysis, local visualizations, you can create specific dashboards for local operators that are different than the dashboards that, say, a multi-site manager would need to see the overall health of, let's say, all of the oil rigs that person's responsible for. And this is what I call a data layer architecture. So I've got a data layer that runs from the very edge all the way to the back end, and I can collect, I can analyze, I can visualize my data at any point along that data architecture, right? So I have edge collectors, but they're not just data collectors, they're actually capable of doing analysis and visualization and alerting at the edge. I can downsample my data from there, so if I have an expensive satellite uplink from an edge node, I can downsample my data and I can save tremendous cost by only uploading downsampled data rather than the highly granular. Let's say if I'm collecting data every millisecond, I may not need that millisecond level granularity when I get to the back end. So I can downsample that data to be, let's say, a 1 minute average and upload that data, and it takes much less bandwidth and is much lower cost. So this is what I sort of term a rational IoT architecture, right? I've got sensors at the edge, and I can have sensors of any kind. I can have Bluetooth sensors, I can have Wi-Fi sensors, I can have LoRa sensors. It doesn't really matter what kind of sensors I have at the edge, right? And I can connect those to an edge collection device, and that edge collection device can then upload that data to the cloud, to a back-end system, and give me data visualization. And when I talk about where InfluxData comes into this, one of the reasons I actually work at Influx in the first place is because I've been doing IoT for a very long time, and Influx was sort of the first platform that I found for data collection and data analysis that I could deploy across a wide architecture, right? So I can deploy the Telegraph data collection agent both at the edge and in the back end, and it's the same collection agent, and I can deploy it distributed so that I can do my data collection, a high-speed, highly accurate data collector at the edge, and I can collect my data sort of wherever it comes. I can run InfluxDB at the edge, and I can run InfluxDB in the back end and at the cloud. And you may say, well, how small a device can I run InfluxDB on? Well, I've run InfluxDB. It runs perfectly fine on Raspberry Pis. If anybody is unfortunate enough to remember the Intel Edison platform, I actually ran it on an Intel Edison, which is about a postage stamp size processor, IoT-based processor. So I can run my database, my data collector, and my database on very small constrained devices at the edge. So I can do short-term collection at the edge, short-term storage at the edge, and longer-term storage at the back end. I can then run a data processing and alerting mechanism capacitor both at the edge and in the back end. So again, if we're talking about this oil platform model, I can actually collect my data out there on the edge. I can do my data analysis. I can generate alerts for the people that need to see them immediately out at the edge without having to send the data back to the back end, do some processing, send an alert back downstream to that operator. And finally, I can use Chronograph, which is our front end. You can use Grafana if you want. I can use Chronograph, and I can run Chronograph at the edge to build local dashboards for local people who need to see the data that's important to them. And I can use the same Chronograph in the back end to run larger dashboards that can use aggregated data from multiple collection points. The really nice thing about it is it's the same binaries, it's the same software, and I don't have to train different people to do deployments at different places across this data architecture. Right? So I can really have an end-to-end data layer that is all the same and runs anywhere and does the data collection, does the data storage, does the data analysis, and the data display. So I don't really want to turn this into a product pitch, but Telegraph is an extremely efficient data collector. I have run Telegraph on architectures as small as wireless routers, just the collector there. As I said, I can do high volume data collection, highly accurate data collection, and this is really important with IoT because IoT generates huge volumes of data. I was hoping to actually give you a demo, but it looks like the network in here is not going to cooperate with me. And even just locally with a couple of sensors, I can generate a fair amount of data. It's really easy to deploy. This is one of the things that I liked about it from the beginning was that I could deploy this across an entire architecture very simply. It's not a difficult deployment. It's not like trying to get Oracle database up on an edge device, right? Good luck with that. And I can run these dashboards and visualizations anywhere. So here's one of the dashboards that I typically run. And if you want to come find me later, I can get my demo working and I can show you this dashboard live. The really cool thing that you may not be able to see in this upper one up here, there's actually two lines up here. And what I'm doing is in real time, I'm actually doing an ideal gas law calculation in real time based on incoming sensor data. So I'm collecting CO2 data, I'm collecting temperature data, and I'm collecting pressure data, and then I'm doing an ideal gas law calculation in the display in real time. And that's a pretty powerful thing to be able to do, and I can do that all the way down at the edge. I can do that pretty much anywhere along that entire data architecture. Right? The other thing that I can do is I can monitor the platform. And monitoring the platform itself on which your data collection is running is really important. Right? If you're collecting data over Wi-Fi from a bunch of Wi-Fi sensors and one of your sensors goes offline, you need to know why that sensor went offline. Did the sensor die or did the Wi-Fi die? And it makes a difference because if I have to roll a truck out to some remote location and send somebody up into a ceiling somewhere and I have to send a specific size person to find that sensor, it really makes a difference if I have to go replace that sensor or if I just have to call a local person and tell them to unplug and then plug back in the Wi-Fi, right, to get my data back. So being able to monitor the platform that it's running on is really important. And so I can do those two things simultaneously on the same platform. I can monitor the platform and I can monitor the sensors. Now I'm going to go out on a limb here for a minute and talk a little bit about something new that we're doing, which is a new data query and analysis language called Flux. If you haven't heard about Flux, I would encourage you to go to InfluxData.com and look up Flux. It's not designed to be an Influx-specific data language, but it is a language that we have developed and are now beginning to use for all of our data query and analysis on InfluxDB. It is a functional data scripting language that will look to a lot of people a lot like JavaScript. It's written to be all of these things: usable, readable, composable, testable, most importantly, contributable and extendable. so that if you need a function that's not already in the language, it's simple to write an extension to the language to do what you need to do. One of the examples of this that I'm actually using is there was no mechanism for InfluxDB, the new version of InfluxDB, to output data to an MQTT broker. And in a lot of the IoT work that I do, I need both input from MQTT and output to MQTT. And so I went and in the course of a couple of days, I wrote an extension to Flux to be able to output data from InfluxDB to an MQTT broker. And it works actually quite well, and it was not difficult to do. It's all MIT licensed, so you can pretty much do what you want with it. I'm going to give you a little bit of an example of collecting data from an Arduino sensor. I don't know how many people in here use Arduino. There has been for a number of years an Arduino Native library for InfluxDB, but that was only good for InfluxDB version 1.x, and we are now transitioning to a 2.0 version of the product. So it became necessary to have a version of the library that was good for 2.0. So this is an example of actually using the 2.0 version of the InfluxDB client library. It's maintained by somebody in the community, and I wrote the extensions for InfluxDB2, and there's a pull request into that library to have it incorporated into the final version of the library so that you can use either version 1 or version 2 and write data to either one of the databases. It's really simple to set up. It takes a couple of calls to set up an InfluxDB object to have either version 1 or version 2 and all of the parameters that you need for those, and then you can actually begin batch writing data. And this is a snippet out of a sensor that I've got in my bag to collect pollution data and send that pollution data directly to InfluxDB. And again, I have my demo up here. For some reason, it's just not working. I think too many people are using the Wi-Fi. I'd love to show it to you afterwards. If you want to come find me, there's an empty room over to the side over there that I'll plug all this stuff in and get it working. So when I'm talking about this data layer and talking about InfluxData, InfluxDB is a time series data platform. And one of the reasons, again, that I work at InfluxDB is because I've been doing IoT for a long time, been looking for a solution for IoT data, and when I found it, I just went to work for the company. It seemed to be the easiest solution for me. IoT data is time series data, right? If you get a definition of time series data, it is basically an event or a reading with a timestamp. And that is what IoT data is, right? I'm collecting temperature data, and I'm collecting a series of temperature readings over time. They're all time-stamped. That's time series data. IoT data really needs to be these three things. It needs to be timely. I need to be able to collect my data in a timely fashion. I need it to be up to date as it's collected. It's got to be accurate. Right? If I'm collecting temperature data and it's off by 10 degrees, it's really not doing me any good. And the most important one is that IoT data has to be actionable. Because if I'm just collecting all of this data and I'm not doing anything with it, then I'm really wasting time. The example I give of this is a manufacturer that I worked with that was collecting all this vibrational data from all of their shop floor machinery. And they weren't doing anything with it. And one of their machines, a bearing went bad on their machine, and the machine shut down, and they had to shut down the whole factory floor while they ordered a part, got the part in, fixed the machine, brought it all back up. It cost them millions of dollars to shut down the factory for a week. And when we went back and looked at their IoT data that they were collecting, we could see that that vibrational data had started to indicate weeks in advance that that machine was having a problem. But they weren't doing anything with that data. They were just collecting it and storing it. So it wasn't actionable. Had they been monitoring it in real time, they would have been able to see that that machine was starting to have a bearing going bad, and they could have ordered the part in advance, had it there. They could have shut down just that part of the factory for a very short amount of time while they fixed that machine and brought it back up, and it would have saved them millions of dollars. But again, they were just collecting their data. It wasn't actionable. So out of all of those three things, having your data be actionable in IoT is probably the most important. If you're not able to take action on your data, it's just a waste of data. It's a waste of space. There's really no reason to collect it if you're not taking action on it. And IoT deployments are really struggling to find a data platform that can handle this. I can't see a show of hands, but how many people have used MongoDB for collecting their IoT data? Right? Don't do that anymore. It can't keep up. Right? If I'm going to be writing millions or tens of millions of data points per second, I need a time series data platform that can handle high write loads, high query loads, and handle the visualization of that data so that it can be actionable, so that it can be timely and accurate and actionable. And I'm actually done on time. Yay! I don't know if anybody's posted any questions.
I have a personal question about a part of that. So, when you speak about the actionable quality, what kind of actions it is able to do? I mean, what computation it is able to do with that kind of platform? Because anomaly detection, I think, is a very costly action. It is able to do that in a reasonable time?
Yes, in fact. So I showed you that dashboard of doing a real-time ideal gas law calculation, right?
Yeah.
So that's actually, it's not a super complicated calculation, but I'm collecting data from two different sensors, and I'm having to bring that data all together in one place, merge that data together, do the ideal gas law calculation, and then display it. And I'm able to do that in real time, right? Okay. So alerts can be done the same way. And if my demo was working, I have this little display up here that should be displaying the CO2 content in the auditorium here. Yesterday, I gave a workshop on InfluxData, and in the room, the CO2 content was almost 4,000 parts per million, which is alarmingly high for having humans being able to actually think and do things. Anything above about 1,000 parts per million and decision making is compromised. So if you're in a meeting and CO2 content is over 1,000 parts per million, you really shouldn't make any complicated decisions. And so I have alerts for that. And I bring my sensor with me to meetings and I look at these things, and when CO2 content goes up, I typically call a timeout in the meeting and tell people that we need to take a break so we can get some oxygen in the room before we make some stupid decisions, right? So being able to have those alerts in real time is, now that's just in a meeting, right? We're just making decisions about, you know, whatever we're doing that day. It's not life and death. But being able to make the same sorts of decisions based on incoming, let's say, pressure data on an oil rig, that is life and death, right? If the pressure gets too high, the oil rig explodes and we have an environmental catastrophe and people die. So being able to do those things in real time is really important.
Okay. I'm going to check if there is questions. Yeah, we have one. What is the trade-off between the number of sensor sample rate and the size of processor deployed in the field? Do you envision the focus moving to data processing before collection for large-scale IoT deployments?
The trade-off in size is, well, I know I sort of went after MongoDB there, and I apologize for that, but I'm going to do it again. We ran some benchmarks on data collection of InfluxDB versus MongoDB on the exact same hardware, the exact same architecture, the exact same data set. MongoDB ingests about 24,000 data points per second, which sounds really good. InfluxDB, and this was our version 1.7, ingests data at 1.4 million data points per second for the exact same architecture, exact same data set. So it's pretty high volume ingestion of data, right? And one of the other things to look at, and in the same benchmark, we looked at what does it take to store that data on disk. MongoDB took 16 gigabytes to store that data set on disk. InfluxDB took 154 megabytes. That's a fair difference, right? And storage isn't free. So when you're looking at total cost of deployment, you've got to look at how you have to scale your architecture and what's it going to cost you. And I say it this way, MongoDB and MySQL and various other databases are great for what they're built for, right? But they're not built for high-speed ingestion of time series data. Time series data is different. It's kind of specialized. And that's what InfluxDB does. It's all InfluxDB does. If you're trying to build a transactional data system, I will tell you first thing, do not go anywhere near InfluxDB. It will not be able to do that. Same if you're doing a document store or anything like that. So it's about using the right tool for the right job. And if you have time series data, which is IoT data, you really need a specialized time series data platform to ingest that, store that data, query that data, and display it.
Thank you very much, David.
Thank you.